In this video, together, we want to take a quick glance at the concept of learning how to learn in machine learning. By that, I'm specifically referring to the concepts of bi-level optimization and meta-learning. The well-known use cases and applications of this is learning a set of hyperparameters, doing few-shot learning, searching for architecture, and things as such. It is important for this discussion to review certain mathematical concepts first before proceeding further with the discussion. Consider you have variables x and z, and imagine that you have a function f which takes as its arguments x and z. Now say that z itself be a function of x, for example z being sine of x times x squared. Now a question that is related to the concept that we want to review is, if you want to find the partial derivative of f with respect to x, noting the dependence of z on x given that z is a function of x, how and what would be the form of this? The final form for this derivative can be written as this. First, we would have something that we call implicit gradient. What that means is that in the expression of f, consider all the z's to be constant and then derive the resulting expression with respect to x. This cross sign here kind of indicates that this is derived this way. And then the next one would be basically the chain rule. This time consider the x's out of the proportion and then derive it with respect to z times the derivation of z with respect to x. And this would be the explicit gradient. One way to intuitively understand why this is like that is that if you take the expression of f by x and z, it would be something that you could use, let's say, Taylor approximation to write the f of x and z something like this. So you would have I from 0 to infinity, you have x to the power of I, and then here you would have something which is a function of z and I, basically, times x. Now if you take this, this would be the expression of fx. Now if you want the partial derivative of f with respect to x, what you will have is that first of all you will have the derivation of the multiplication of two functions. One of them would be the x to the power of I, and the other one would be, let's say, giz, which is giz of x, or in some sense gioz of x. So the first term that we will have in this derivation would be this. If you take a look at this, what this means is essentially the implicit gradient. And then the next component would be I from 0 to infinity. You would have xi, you would have rho this, basically the chain rule. And this would basically be the explicit gradient. Now, an important case example that we want to review is the paper titled Differentiable Architecture Search, which is known as DARTS, and it's one of the famous case examples of using meta-learning. In a nutshell, the paper is like this. You have a set of, let's say, hyperparameters called alpha. Those would determine the structure of your network. So imagine you have a network parameterized by different things. Let's say at each component you would have, let's say, different lanes, and alpha would be the parameter choosing which lane to choose to pass the data through. And let's say each one of those lanes correspond to a different operator. This way you have an architecture that basically you are gating different parts of it using this hyperparameter set alpha. And the goal is to optimize the parameters, basically the model weights, let's call them omega or w, and the alpha, which are the gating parameters that determine the structure. And this way you are looking for the optimal architecture using differentiable programming and essentially gradient descent. So then again, you have the hyperparameters determining the architecture, and you have the network weights. Now this is the paper. And again, the goal is to optimize alpha, which determines the architecture, and omega, which are the model parameters. If you write the optimization objective, it would look something like this. So the ultimate goal is to find the architecture. Remember, the paper's title was Differentiable Architecture Search. So the goal is to find the, let's say, optimal architecture for a certain task. Let's say, okay, so the goal is to find this optimal alpha. So in order to do that, we would have, let's say, a validation loss. Let's say you have a data set. you determine a certain type of criterion on it, let's say cross entropy or something like that, and then you call this validation loss, let's say, and this would be the L of val, and the inputs. So what this would be the function of is omega star of alpha and alpha. So you want to basically explore this space and find the alpha as the argument that minimizes this expression here, such that in each one of these cases you want to have the optimal parameter set for this alpha. Now you can see there are two levels of optimization here. One is this alpha, and the other one is spanning over omega, corresponding to a specific alpha being optimized. So because of these two levels, they also call this bi-level optimization. This is the meta loss, or the loss that you're using to optimize alpha, and then this is going to be the normal training loss that, let's say, if there was no alpha, or alpha were a set of fixed hyperparameters, you would use this to optimize the model weights. Remember that the intuition is that the ultimate goal is finding alpha star, which in other words is the optimal architecture for this task. If you imagine that this condition, namely the set of parameter weights used in each evaluation of L-val, be the optimized set of parameters for alpha, say this condition is magically satisfied. Then you can say that this expression, namely the main optimization objective, says that you want to go over all of the different architectures, and then for each one of them pick the optimized parameter values, meaning that optimized with respect to that architecture in order to minimize the training loss, and then use this validation criteria and now compare these different architectures this way. Now the solution that Darts in the year of 2018 proposed is this. You want a gradient-based optimization of alpha, in other words, a differentiable search. Therefore, you want to basically compute the gradient of this validation loss, or this meta loss, with respect to alpha. And remember, the arguments of that are omega star of alpha and alpha. Remember the concept of f of x and z. In that context, alpha would be x, omega star of alpha would be z, which is a function of alpha. Now, solving this would be difficult if you want to reach the 100% accurate result, because you would have to, for each alpha, train the model fully and find the optimal parameter weights omega. Therefore, in order to make this problem tractable and find an approximate but great solution, we are going to settle for an approximation of this omega star. Given that fully optimizing that nested loop is going to be computationally expensive, one approach which is widely used is to do a one-step look ahead of the gradients. What that means is that you approximate the optimal set of parameters given, let's say, a specific set of hyperparameters alpha. So omega star of alpha will be approximated by one-step gradient descent applied on omega. So omega here was not necessarily a function of alpha, because we're just doing one step of jointly optimizing omega and alpha. So we have omega, we have the L train, which we were using in order to optimize omega. So we would compute the gradient of this with respect to omega, and we have a learning rate. We do this, we add this additional gradient step to omega, and this would be the approximation of omega star. So again, note that the initial point, this omega, given that we're doing one step look ahead, is not a function of alpha. If we were to use, let's say, multiple steps of look ahead, then omega would also be a function of alpha in this case. Now, this here would be the learning rate, which is used in the learning phase, or something that we would basically add here in order to do the one step look ahead for omega and have the approximation of omega star. Note that when we were talking about L train being a function of omega and alpha, what we mean is that basically in your training objective, you have some sort of an objective such as this, meaning that you want the expected loss of basically observations and labels sampled from the distribution of observations and labels. You want this expected loss to be minimized, and this, for example, could be cross-entropy criteria, in which F would be your model, taking X the observation, and parameterized by omega and alpha, it would predict logits for it, and then we would compare them with the given label Y and compute the cross-entropy results. So what that means is that basically the loss that you will have, given that these X and Y's would be, let's say, empirical risks and would be computed based on the data, ultimately the L train would be the function of omega and alpha. Now we want to optimize and find the alpha, right? So in this case, we have the validation loss by which we wanted to train alpha. And therefore, given that we want to use this in a differentiable setup and find the derivation of L-val or gradient of L-val with respect to alpha, we have this kind of format right here. Now, remember that in the discussion of f of x and z and implicit and explicit gradients, we had alpha being x and omega star alpha being z. So the first thing that we want to have is the implicit gradient, in which we assume that the omegas are fixed and constant, and then we derive it with respect to alpha. And this was the implicit gradient. Now, one question that we would have is how to compute this here. Now, in general, for computing this component and other components such as this, in practice you use the autograd. And in order to compute, for example, the derivation of L with respect to omega at a certain point, you parameterize the model with that and you do the backpropagation in order to compute these omega. The same applies when you're dealing with alpha as a specific subset of the parameters by which your model is parameterized. So for example, in this case, you would do the backpropagation on the unrolled model in which for the weights omega, you would have the omega star of alpha, and then you backpropagate to compute this derivation like here. The next terms would be the portions of the explicit gradient. So the first portion would be the gradient of L-val with respect to omega star, given that omega star and alpha. Remember the f of x and z thing here. In this case, we just remove this alpha from the arguments of omega star, and we are computing this. And lastly, you have this. And again, using backpropagation, you could compute this, and this one also, given the function, given the omega star being a well-defined function of alpha, given the assumption of one step look ahead of the gradients, you could also compute this one as well. So to compute this one, we have to remember that this was the approximation formula. So we have the approximation of the omega star of alpha being omega minus learning rate times the gradient of L train with respect to omega being a function of omega and alpha. So L train is a function of omega and alpha, and this entirety would be a function of omega in some sense, and you're deriving it with respect to omega. So if you now want to derive this formula in this expression right here with respect to alpha, you would have it like here. So omega itself, given that this was an initial point, which wasn't initially a function of alpha, we remove this, and the derivation of that with respect to alpha would be 0, so it doesn't appear in here. And then we have this term over here. So what happens here is that we are going to have a second order gradient like here. This learning rate here would be removed from that, so you would have this term right here. And now this thing right here, if you, for example, look at this gradient of alpha and omega, it would be a Hessian, and it would be of the order of the cardinality of alpha times the cardinality of omega. So for example, if you have 10 weights and 5 hyperparameters, it would be like a 5 by 10 matrix. Now this thing would be a little bit costly, so we will learn how to approximate this soon as well. Again, for computing this component, we would say that, okay, we want to find the derivative of this L-val with respect to omega star. So what we do is that we parameterize a model with omega star, or let's say the one-step approximation of it, and alpha, and then we use the backpropagation with respect to omega to find this derivation here, and this would be this. And now, given these expressions right here, we have a complete picture of how to compute the derivation of validation loss with respect to alpha, which then can be used ultimately in a gradient descent step in order to iteratively optimize alpha and find the optimal architecture or the configuration corresponding to an optimal architecture. One concept that is used in the Dars paper is the concept of finite different approximation of derivatives. Now this is a very familiar concept. You know that if you want to derive a function f, which is a function of x with respect to x, you can write it as a limit h approaching to 0 of x plus this step h minus fx divided by h. Now this thing is also called forward difference, given that you have an x, you push the x forward and basically pick the point x plus h, and because of this x plus h and x plus 0, you would have the forward difference. Similarly, you have backward difference in which you have x and x minus h instead. and central difference, in which you have x plus half of h and x minus half of h. So it's going to be, this bound is going to be centered around x. Now, if you have the function f of x and z, similarly, you have the derivation of f of x and z with respect to x. It would be f of x plus k epsilon times z, and z, and x minus k times epsilon and z divided by 2k epsilon. So this thing, given that epsilon is going to be 0, would approximate this term. Now you can take this k from the denominator back to here, so k times this derivation would be equal to this formula, approximately. And now this is what we can use in this finite difference approximation to do certain simplifications. All right, remember that this expression was part of the result for evaluating the derivation of the validation loss with respect to alpha. Now, the goal is to approximate and maybe simplify this component here. So on the left, we have this Hessian of alpha omega, and here we have the gradient of omega prime. Now, this omega prime is the same as the omega star in the previous notation. This omega prime is the one-step look ahead of the omega with respect to the gradient of L train with respect to omega, and that is basically what we were using as an approximation of omega star. So maybe it would have been better if I used this notation of omega prime in the previous slides as well. Now, in terms of the order of this, we would have the complexity times basically the dimension of alpha times dimension of omega. For example, if you have 10 hyperparameters and 50 parameters, you would have 500 elements, because you would have a 10 by 50 matrix for here. So in terms of dimensions, you would have alpha times omega, and this one would be the derivation with respect to omega, so you would have omega times 1, and then this result would be alpha and 1, which would essentially be part of the derivation of L val with respect to alpha, which we hope to give us a alpha dimensional vector by which we could use in the gradient descent and add it to alpha in order to push it towards the optimal point of the optimal architecture. Now let's go back to the finite difference approximation. So say we have f of omega and alpha be defined like this. So you would have the L of train derived with respect to alpha. It's a function of omega and alpha, okay? Now you want to derive it with respect to omega here. And we want to multiply it by a k. Now, spoiler alert, this k would be this term here, which would be the gradient of L val with respect to omega prime. Now note that given that f was defined like this, gradient of it with respect to omega would result in this Hessian right here, this term right here. And in order to use the finite approximate theorem, we would consider this k here, and we would put a 2 epsilon on the denominator here. We want to use, let's say, the central version of the finite difference approximation. And in the denominator, we would have omega plus something and omega minus something as being the 2 points indicating basically the span that we are signifying. And with that being small, basically would be similar to putting the limit here. With that being small, this would essentially help approximating this term here. So omega plus and minus something would be plus and minus epsilon times this term, which was the k here. And this term was the gradient of L val with respect to omega. Now, in this case, you only need 2 back propagation and 2 forward propagation in order to compute this. And this would reduce the complexity from omega times alpha to this term. Another case example is perhaps the most famous example of meta-learning, called model agnostic meta-learning, which the goal of it is to perform an optimized few-shot learning, meaning to find a set of parameters regardless of the model architecture, but having a specific, let's say, model families on which we are performing this MAML. So the goal is to find these parameter weights in a way that going from task to task, the result it's going to result in efficiently learning those tasks. In other words, a perfect example of learning to learn. Imagine f is your neural network, theta being the parameters of that neural network, mainly the weights. Here is how MAML works. In terms of how the optimization takes place in the context of meta-learning, all of these models are pretty much similar in the sense that you use this sort of gradient look ahead in order to approximate the inner loop, and then you use that approximation in order to optimize the outer loop. So that's essentially how it works. Now let's go over the main algorithm of MAML, model agnostic meta-learning, and see how exactly it works. Let's say you have a model f, and f is parameterized by theta, theta being, for example, the weights of your neural network. Now what you want to do is that, given that you have a distribution over tasks, each one of those tasks, for example, be kind of like an image recognition task or something like that, you want to find the thetas in a way that, going from task to task, it is optimized for learning different tasks, or in other words, it has learned to learn. You have alpha and beta being the step size parameters, and we will see how they are used. You randomly initialize theta, which happens when you initialize a neural network, and then you do this loop. Now, in this loop, you sample a batch of tasks from the set of tasks. And then for these tasks, for each one of these tasks, what you do is this. You have k examples. So if you, for example, have n tasks and k examples, you would have a n-way k-shot problem. So you have k examples for each one of these tasks, and you compute the gradient of the loss of this task I with respect to the parameter set theta. So this would basically be the step that you would have in order to optimize, if you wanted to optimize theta for that specific task iteratively. So you do one step of gradient descent using the step size alpha and this, and then for task I, you retain a, let's say, one step look ahead of theta, which you would call a theta prime I, which in some sense would be the approximation of optimizing theta with respect to this task, and you keep it. So you compute the adaptive parameters with the gradient descent, you keep it like this. Once you do this for all these tasks in your training, now you update theta with the step size beta. What this means is that in this step size beta, you basically compute this thing here, meaning that for each task I from this distribution, so for each task I, you take the model, let's say your neural network, you put the theta prime of I in that, which was the one step look ahead of that. And now you have a model which is parameterized with the approximation of the optimized set of parameters for that task. You compute the loss of that task, and then you sum them all up together. So this would be, let's say, something similar to the expected loss of these over tasks. So this here, let's say with a normalizing factor, would be the expected loss that you will get for a task, and then you would want to drive it with respect to theta in order to optimize the theta. So in this loop, you are learning, and in this outer loop, you're trying to learn how to learn. Let's read this part again. So in this case, in the inner loop, the goal in this optimization intuitively is that you have the loss of tau I, which determines the performance of the model on task tau I, okay? You want theta to optimize that, meaning that you want theta to go in a way that the loss on the task I gets minimized. So this is for the inner loop. So for each task, you would have this thing. Now, the outer loop, if you look at this as, let's say, the average loss of this updated parameter weights on these tasks, you want theta to move to a direction in which, on average, with a small update, it performs well on all of the tasks in some sense, or result in an optimized expected loss over these tasks. So in other words, this one is going to put the theta in a position that is more well positioned with respect to all of these tasks together. And this in general is how the MAML works. The next example that we want to talk about is a paper by Microsoft called Meta-Label Correction for Learning with Noisy Labels. The idea is that you want to use meta-learning to learn a label corrector network that takes in the given label and the representation of the features of the data, and basically provide a label that is kind of like more informative for training a model to perform a certain task. The objective of this optimization is written like this. Again, it's a bi-level optimization. What you have here is that you would have a clean subset of data that you would use as the validation set. Let's call it the distribution corresponding to that to be D, or the data set D. And here you would have a D prime for training as well. Now, Here you have y prime indicating in the d prime the labels could be noisy. F is, let's say, your neural network, which is parameterized by models omega. And G is a label corrector, which is parameterized by alpha parameter set. And the goal of it is that it takes the output of the model on a given observation, let's say the features extracted by the model, and it takes the given noisy, possibly noisy label y prime, and it's supposed to output a label for you by which you would train your F. And then you would use meta-learning to learn this label corrector. So what you have is you would have, let's say, so expected value of loss on basically observations and labels being sampled from a data set is a pretty generic way of writing the loss function. So here on this mini clean set, you would have the clean labels and you would have the F, and the goal is to learn alpha in a way that once you have the label corrector that is parameterized by alpha, and once you get the labels from that and optimize omega accordingly, if you put it there, it's going to result in the best result for the small clean subset as well, with G being the label corrector that is parameterized by alpha. Now let us look at the mathematics of the meta-label correction work and see what exactly is the solution that they propose to this bi-level optimization problem. Similar to the approaches that we discussed before for DARTs and MAML, what they do again relies on approximating the optimal solution to the inner loop and then using it to optimize the outer loop. So in the one-step look-ahead setup that we had, you had a parameter set W and you had parameter set alpha. In the case of MLC, alpha determines the basically denotes the set of parameters associated with the label corrector network or the meta network. And omega is essentially for the classifier or the original basically model that takes in the observation and outputs the prediction. D prime, as discussed, was the data set with the noisy label, and D is the data set, so the D, not the D prime, is the data set with the clean subset that is used in the loss for the outer loop. Now, in the case of the one-step look-ahead, you have the W prime of alpha, which is the one-step gradient descent look-ahead of the W, or omega. It is found by using the learning rate eta, gradient, like driving the LD prime with respect to omega, and then using it in one step of gradient descent to get to this, which results in the W prime or omega prime. I refer to this as omega again. Omega prime is going to be a function of alpha. However, they mentioned that given basically the problem that they are facing, which is doing this type of label correction, doing just one step of gradient descent and this one step look ahead might not be super efficient. In fact, they do propose a approach that is going to be relying on k steps of gradient look ahead, and then they show that, for example, around 10 results in the best empirical validation performance. Now, if we go beyond one step, you would have this kind of like a same formula. However, this time this omega, the initial point of view, also is a function of alpha, because previously it has gone through additional gradient descent steps. Therefore, it already has been a function of alpha. And remember, the gradient descent that is applied on omega is basically resulting from the derivative of the gradient of this LD prime with respect to omega, which this omega itself was a function of alpha in this case. And note that again, you have this alpha here because this alpha is going to determine the meta network and determine the pseudo labels that you will find in order to train your network with, which results in basically this term to be a function of alpha, even if this omega isn't. So when it's applied once, this omega itself, it becomes a function of alpha. All right, let's look at this formula again. So in order to find the omega prime, you do this formula right here. So this is eta, this is alpha, this is omega, which we assume right now to be a function of alpha, and you have this omega alpha. The ultimate goal of this problem is to optimize alpha, okay? So we are interested in basically looking at this and seeing what exactly would happen if we derive this with respect to alpha. So we add this partial derivative over here. So we have this, let's say the Jacobian of omega prime with respect to alpha. So what you have here is that this derivative is going to be written like this, given this recursive formula. So this is going to be derivative of omega with respect to alpha minus eta, the learning rate. Now, this part is important. So we want to derive this with respect to alpha. However, this omega itself, we are assuming that it is a function of alpha itself because of the previous gradient descent steps. Now that we have this, we could go back to the explicit and implicit gradients and those definitions and see what we can write it as. So we could see that the f in that context is going to be this term, basically the gradient of LD prime with respect to omega. Now the dimension of this term is going to be omega times alpha. And let's write it down and expand it. All right, so the first thing that we are going to have is this, in some sense, the implicit gradient. So we kind of remove the alpha component from omega because we're assuming this omega is going to be fixed. And then we would drive it with respect to alpha. So this is going to be the gradient. So this is going to be the alpha omega. This is going to be this Jacobian right here. And then the next term, this Hessian right here. And then the next thing that we are going to have is this term, which is you derive it with respect to omega again. So you have this Hessian right here times this term. Now in terms of dimensions, the first one, this is going to be omega times alpha. This is going to be omega times alpha. This is going to be omega times omega times alpha. Again, all of this is going to be resulting in the same dimension for this, which was omega times alpha. Now in the notations of this paper, they refer to this Hessian as the edge of alpha and omega, and this one is omega and omega. And therefore, we'll write it like this. So you have the derivative of omega prime with respect to alpha. It's going to be I minus this diagonal matrix lambda over here times h of double omega omega times this derivative minus this, again, lambda matrix times h alpha and omega. If you look at this, what you will see is that, yeah, you essentially have the same thing because you have this term. You can factorize this and you can bring this out, the derivative of omega with respect to alpha. So when you bring it out, you have this I here, and you have this minus eta, which they kind of like, to break it down for each parameter separately. So you will have this diagonal matrix. And then you also have this omega omega Hessian, which is this term that they show it here. And then they also have this eta here, which brings this lambda here. And this term, which is this Hessian. Again, this lambda is the diagonal matrix, which is the omega by omega dimensional matrix of learning rates for each different parameter in your network. Now, in the notation of the paper, they define g omega prime to be this term. So it's going to be the gradient of the LD. Remember, D is the clean validation loss. If you put the omega prime or the approximate, let's say, solution to omega here, you have alpha 2, and you derive it with respect to omega prime. They call this g omega prime. Now, if you do the g omega prime times the, partial derivative, basically the derivative of omega prime with respect to alpha, in terms of dimensions, let's say you write it like this to be this Jacobian of 1 times omega, and then this one is omega alpha. The result is going to be a 1 bar alpha thing. What does that remind you of? It's going to remind you of this term, which we are going to use in order to optimize the alpha or to move it towards the optimal point. So here is going to be the derivation of the LD, D again, the clean loss, when you put the omega prime parameterization in the model, alpha with respect to alpha, because of the chain rule. Now, if you use the formula you found before, you would put this g omega prime here and g omega prime here. Now, in order to find out what exactly would be this sort of update rule, we need to work on kind of computation of this and see if we can find an approximate for this. Once we do define that sort of approximation, we could use that along with the case step inner loop optimization in order to find the best result for alpha. One thing to note is that when I'm saying like the best result or like moving toward the optimal point, we are talking about the context of non-convex optimization. It's not necessarily going to be, let's say, the global optimal in the manifold of loss, but yeah, it's just training the model towards a point that gets great performance. Now, how can we approximate this formula here? So the first thing that they do is that they take this Hessian of omega omega, they set it to I as like a way to approximate the result. When you're talking about this derivative right here, you could write it like this. So you could use this LD of omega and alpha, okay, LD of omega and alpha, and you could use chain rule and write it like this. Now, if you invert this one, it's going to be what? It's going to be is going to be g of w, because g was defined as the LD, okay? And as a derivative of LD parameter. So g of w was defined as the LD parameterized by w, okay? Or omega, sorry. I keep, using these two terms interchangeably, but, yeah. Omega and w, I both refer to this by them, okay? So now because this one is inverted, we're going to use the pseudo-inverse of GW, which is this term right here. It's going to be GW transposed divided by the norm of it squared. And therefore, we could have this first part of this formula figured out. Now let's go on to the second part, which is GW prime and lambda h alpha w. And again, note this definition of G of W prime or G of omega prime. Now in terms of dimensions, we know that this one is going to be 1 by omega, omega by omega, and omega by alpha, resulting in a 1 by alpha, which is the thing that you're going to use, the dimension that you're going to need in order to find the gradient of the final gradient with respect to alpha that you're going to use in order to optimize alpha. So you have this term here. Now if you open this up, you're going to have basically this term like this. And now usually the goal is to kind of not do these types of backpropagations multiple times and try to kind of go from multiplicative orders to orders of complexity to additive orders of complexity and things like that. So you can sort of bring this alpha out of here and you will have these terms. And therefore deal with this instead. And again, sorry for any sort of confusion resulting from me kind of using Jacobian and gradient dimensions and things like that kind of interchangeably in here, but it's not generally too difficult to understand the relationship and kind of their placements in these propositions. But yeah, in general, this simplifies that, and then I use this update rule to optimize alpha. Now we want to go one step further and look at, let's say, how to code a meta-learning solution. And we're going to focus on these 3 case examples that we discussed, and we want to look at their code and how exactly they were being done, so to kind of obtain a better perspective of how to code, let's say, a meta-learning solution and, help ourselves in developing our own. Let's look at the Dart or differentiable architecture search's official code base first. If you go to the CNN folder, for example, you're going to see a bunch of files here in which this architect file is going to have the main components of the algorithm. Inside that, you're going to have this architect class, which is going to contain all of the methodologies that you need. The first thing you want to be concerned with is going to be the unrolling the model, or kind of doing that approximate, optimization of the inner loop. The first useful tool in this context is the construct model from theta function, which essentially means that you give it a parameter set of, basically the set of weights, and it would insert it into a model. So it's kind of like load the state dict, except that this theta is going to be a vector, so they have to kind of know when you're, let's say, going through the named parameters of the model, you're going to have to find out the number of parameters that layer or that component had, and basically bring them out of the theta and put them in the proper position. And basically they create this dictionary params, and then they update their model dict with it. So model dict is going to be like this, and then they update it with that, and then they load it into the model new, and then they return the model new, and model new is this. Next, you have the compute unrolled model. In this part of the code base, you're computing the omega prime in some sense. So you have theta, you find this basically update to it, and then you basically subtract eta times that update from your theta, and then you use that tool we just discussed, construct model from theta, to create the unrolled model, or in other words, the model with the updated one-step gradient look-ahead approximation of the optimal result for the inner loop. Next, you have this outer loop in which you essentially have the unrolled model, you compute the unrolled model, and then you compute this loss of the unrolled model, this time on the validation component, and you get this unrolled loss, and then you do the backward of that, and then you compute this d alpha and vector. So if you go over the alpha, which in this time is going to be architecture definition, the architecture defining parameters of your unrolled model, so the gradient of those are going to be this d alpha and the vector in this case is going to be the the value of the parameters for all of the model parameters. Now you want to compute also this implicit grads, which gives you which this function gives you. So you put this vector in here, input train and target train. Now the way this one works is like this. First you have this epsilon here, which is defined by this r here divided by the norm of this concat vector. Okay, then do you remember that plus minus thing? So if you don't remember, please go back to the video where we were discussing the finite difference approximation of the gradient. So you have this model loss, input and target. Remember, you're adding this term, you're adding r times v to this p, okay? And you're essentially creating the omega plus here in these parameters, and then you're driving it. So one a back prop and then another back prop here. So you have the omega prime defined here, omega plus defined here, and omega minus defined here. And then you're going to have these two gradients, positive and negative, and you're going to basically put the p back into what it was, and then you have x minus y divided by 2r as like the finite difference approximation of the gradient using this grads p and grad n, and you're going to send this out as this result. Now let's come back here. Again, note that the on-road loss is going to be L val of omega prime. So first you have this implicit gradient of L val per alpha, which is found like this. And then you have this derivative with respect to omega prime, which is like this. And remember the part where we had to like use the finite difference approximation to compute in the part of that gradient. So it's computed using this one. And finally, you have this eta that you use. And again, this is the step function, which if unrolled, it computes it like this. If not unrolled, computes it like this, and it steps the optimization forward. And that sums it up. Now let's take a look at the model agnostic meta-learning. Now learn to learn is one of the nice packages for meta-learning. The other packages are things such as Facebook's Hire, which I think is no longer maintained. But there are like several packages, and a lot of the papers like MLC that we will discuss shortly that they implement their own codes. But yeah, mostly these packages are kind of wrappers on Torch Autograd and things like that to kind of help you be able to do these things in a nicer, more clean way in your coding. Now let's look at the core component of the MAML code. So first you sample a task from basically the train tasks, and you run the fast adapt function on this, which means that you would split it into a training and evaluation, and you do the adaptation to get to theta prime. You get this validation loss like this in the evaluation error. Now this backward here is going to be the outer loop optimization for optimizing the model in the outer loop. Going to the fast adapt, you have this splitting here, and here you would have for adapting the model. So you have some certain adaptation steps. In each adaptation step, you take the learner, you give it the adaptation data, you give it the adaptation label and the loss, and you get the train error, and then you use this adapt function, which is an important thing. It updates theta, but it does not touch the gradients of the model, because given that both in the outer loop and the inner loop, in the model agnostic meta-learning, you're focusing on the same set of parameters, you need to kind of do this in order to not kind of optimize them wrongly. So this adapt thing is going to give you this new parameters, but it doesn't going to touch the gradient. So it's that. And then you have the predictions, the validation error, the validation accuracy. So this validation error, again, do not confuse error with, let's say, the 1 minus accuracy. This error here is a loss, and it will be returned here. Now let's look at the adapt function. You're going to have to go to this gbml.py in the algorithms component. It's the general wrapper for gradient-based meta-learning implementation in learn-to-learn package. And we're not going to read the entire file, just this part. For example, this compute update here, you're going to get loss, the model parameters and everything, and you get the updates, and then you use this diff SGD on the module with the updates. Namely, the important point here is that you're not doing, let's say, the stepping in the gradient and things like that. So what you do is that you get the updates, and you use this diff SGD internal method in order to compute this and in order to update the parameters. And then you set this parameter updates to true. That's kind of like this sort of adaptation layer, so kind of bringing it out of the normal torch pipeline. Going back to this, then you have a certain number of tasks. You'll also need to optimize this, normalize these parameter gradients with respect to the number of tasks that you have, and then you do the optimization that step, and this concludes the MAML code. And the last portion of it is to do with the evaluating of the meta test error and meta accuracy. Now lastly, let's go and take a look at the MLC's code. So MLC's official code base is available here, Microsoft MLC. The MLC.py is the main module that contains the functionalities. And this step HMLCK, this is going to be the main function that helps you do the case step look ahead thing, which is shown also in this figure right here. So let's take a look and see what it does. As discussed, this is the main function that is going to allow you to do the things that MLC wants you to do. So we are mainly going to focus on this module's content. In this notation here, note that data G is the D in the paper, data S is the D prime in the paper. Mainnet is the classifier, and the metanet is going to be the metanet is going to be the label corrector in the network. Now the first thing you do is you do the GW. This is good naming because in the paper also GW is defined as the gradient of the D prime with respect to omega. Actually, my apologies, this is going to be normal D, not the omega. Then you want to do a computation of the pseudo labels in here. What you can see is that you take, let's say, the D prime and you feed it to the mainnet, you get the logits, and then you feed that along with the possibly noisy labels to the metanet. It's going to provide you with the target or the generated corrected labels, and then you could compute this soft loss F here in order to obtain this loss, which would be the LD prime. Now you have LD prime here, okay, and then you basically derive it with respect to omega, and then you put it at F param grad. So F param grad is going to be basically gradient of LD prime with respect to omega. Now you want this omega prime right here, so you use this update params function to do this step forward with this eta, and then you get this F params new. Now what you do is that now you want to put the omega prime in the model. Basically, so you go and traverse over the main network's parameters, basically the omega length parameter set. You take this f param new, which is the omega prime, you put it inside the param, but you also take the previous value of the param, which is the omega, and you put it in the f param as like a kind of like a record of what they were, which is going to be used throughout this thing. So HW also is a training loss Hessian approximation. They assume this to be identity, so they put it as 1. Now you have the main net, you give it the data G, so this is going to be LD because you're focusing on the data G and D, but now the parameters of the model are omega prime, so this one here is going to be LD of omega prime and alpha, so this is going to give you the largest G, and you have the corresponding loss. Now here they compute the GW prime. Again, GW had to do with the gradient of LD, not D prime, D. So you have the LD, loss G here, and then you derive it with respect to this new parameters. Remember, you put the omega prime in the network parameters, so this mainnet.parameters is going to give you this thing. Let's go down. In the LGW prime here, what you're computing is essentially this component of this. You have the D param S and you have GW prime, and then you're using it to get to this LGW prime. The goal of this formulation essentially is to kind of allow you to minimize, let's say, the number of times you do the backprop with respect to alpha. And you could see that this backward goes right here. And then again, for each one of the metanet parameters, you go right here, and then you add this term. Now the args of the steps is, let's say, so args is one of the arguments that you feed to this system. Is going to provide you with a namespace. This step is going to be updated, so args.steps, I think step would have been a better name. It's being updated by the master process that is running this. Now this is going to be get updated. Gradient steps is going to be, let's say, the k step look ahead. So for example, it could be 8 or something like that. And then if this is reaching that milestone, you do the meta-opt.step, and then you reset this DW pref. Finally, you're going to put the f param, which was your original omega or original w, in the mainnet, and you also put the gradient back in the param, the grad, and this time you can do one step forward. So assuming that this, let's say, is not the case, let's say this hasn't reached that part, in each step you're actually doing that sort of optimization of the model, while also retaining the information that you need in order to do the case step look at approximation for the basically leveraging that in the final analysis and in optimizing the alpha in the meta steps, in the meta gradient steps. So you can arcs to the steps indicates the iteration, and this is the main optimizers update. Thank you so much for watching this video. I hope you have found it useful.